In the next one, I want to do the same thing. I'm going to just identify the common denominator. And for this one, I can just think of this second denominator. That's an x plus 3 times an x minus 3. And so what I'm going to do here is I'm just going to multiply everything by the common denominator, which happens to be that x plus 3, x minus 3. And so what I'm going to do here is I'm going to multiply this entire side by the x plus 3, x minus 3. And when I do that, I essentially distribute. I have to multiply that right here with this first fraction, but I also have to put it right here with this second fraction. And it's important to note that. I'm just going to go ahead and draw it here with that second fraction so that we can see it just a little bit better. Okay, and I got to do the same thing on the other side. I've got to multiply this side by the x plus 3, x minus 3 as well. And so right away we see what's going to happen. The x plus 3's here cancel, so I just have 4 times the x minus 3, which is essentially going to be my distributive property. That's a 4x minus 12. Over here, nothing cancels, so I just have the 2 times the x plus 3 times the x minus 3, which when I multiply all that out should give me a 2x squared minus 18. And then over here, everything's going to cancel, so I'm just left with the 8x. And so now it just becomes a matter of combining like terms and bringing everything over to one side. I'm going to subtract that 8x. So after I combine like terms and everything, I get a 2x squared minus 4x, there it is, and minus 30. Lost track of some of my values. And I'm just going to solve this thing by factoring. This guy is going to head and going to factor. I could build a bridge here. Well, really, for this one, I can just divide everything by 2 first. That might be a little bit easier. So we'll do that. We'll divide each side by 2. So that's going to end up giving me an x squared minus 2x minus 15. And now solve it by factoring. That's an x minus 5. That is a terrible looking 5. And an x plus 3. So I find out that x equals a positive 5 and a negative 3. And as I look back across this thing, keep in mind those original denominators. They would give me restrictions that x cannot equal a positive 3 or a negative 3, which means this negative 3 is an extraneous solution. I can't use it, so I get rid of it, and I just keep the x equals 5. Okay? In the next one, we want to find all these values and then draw a quick sketch of this thing. So I start off with the domain restrictions, which is what I get when I set the denominator equal to 0 or not equal to 0. This factors into an x plus 1 and an x minus 1. So I find out that x cannot equal a negative 1 and x cannot equal a positive 1. So those are my domain values. They're my domain restrictions. And now I'm going to simplify this thing completely. So I go ahead and factor this thing as far as I can. The numerator, I build a bridge. That's a negative 10. Two numbers that multiply together to give me a negative 10, but add together to give me a negative 3 is going to be a negative 5 and a positive 2. And when I do my factoring by grouping and everything, this is what I should come up with. The denominator I already factored once, so let me rewrite that. And what happens here is the x plus 1's cancel out. So my simplified version of this thing is the 2x minus 5 and the x over the x minus 1. And now vertical asymptotes versus holes in the graph, these guys come directly from our domain restrictions. Each one of those is either a vertical asymptote or a hole in the graph. So I look at my domain restrictions. The positive one did not get canceled out. It came from this factor. So the positive one for my domain restrictions is my vertical asymptote because it didn't get canceled out when I was simplifying. The negative one did get canceled out, so that's my hole in the graph. And the hole in the graph isn't just an x value, it's an x and a y value. So I have to plug that negative 1 back into this equation to see what my y value equals. And so when I plug that negative 1 back in, it looks like I get a negative 7 over a negative 2, which is a positive 3.5. Okay? So now for this one, horizontal and oblique asymptotes, these two are also tied together, and it's going to be one or the other. I have to compare the degrees. Up here, the degree is a 2. Down here, the degree is also a 2. Remember, we're looking at the highest exponent. When the degrees are the same, it means that what I have is a horizontal asymptote. So I can get rid of the oblique. And when they're the same, I divide the leading coefficients. Remember, is the number out front, which is the 2, and the 1 down here. So 2 divided by 1 gives me a 2. So y equals 2 is my horizontal asymptote. And now I'm just going to start to graph this thing. I'm going to hold off on the range for a second. But when I graph this thing, I'm going to start with the asymptotes x equals 1. I do a dotted line for that. And then I do y equals 2, again another dotted line to represent my asymptotes. I can plot the hole in the graph at negative 1, 3.5, right about there. And notice it's an open dot. And I could plot some points around this, but I know that this thing kind of has to hug this line and go through that point and hug the other line. Okay? And that kind of gives me a quick sketch over on this end. The other side of this thing, I don't know whether the curve is going to be up here hugging these lines or whether it's going to be down here hugging these lines. And so what I have to do here is I have to gather a little bit more information. I simply just set up an XY chart and I pick a value or two from over there. Maybe I plug in something like a 2 or a 3. All right? When I plug a 2 in, that gives me a negative 1 over 1, which is negative 1. So I get the ordered pair 2, negative 1, which is right here. If I plug something like a 3 in, that gives me a, let's see, a 1/2 it looks like. So 3, 1/2. And so I can kind of get a feel for where this thing is. It's over here, it's down here somewhere. I know it's going to hug those lines because those lines describe the end behavior, and I know it's going to go through those points. All right? And so I end up with my kind of typical rational function graph here. It kind of hugs those lines, not going to touch them in terms of the asymptotes, and it's got a hole in the graph. And so I've already got the domain. The domain was listed up here. X cannot equal the positive 1 or the negative 1. And again, those restrictions deal with the asymptote and the hole in the graph. Same thing with the range. The range, the y values, cannot equal. It deals with the asymptotes and the hole in the graph, but this time it's the horizontal asymptote. We're not going to equal that 2. We're going to get closer and closer to that line and not touch it. And the hole in the graph, I don't have a y value at 3.5 because that's where my hole in the graph is. And so those are my range restrictions. So my domain and range here are pretty easy to find once I have all this information and I have this thing graphed. Okay? If you take a look at this next one, it asks me to find the 5th term of the sequence. And the number of the term is just the n value. So this time I'm just plugging the 5 in. So I have a sub 5 equals a negative 2 times 5 plus 7. And keep in mind the a sub 5, that 5 that's over there with the a value, doesn't really do anything. It's just a label. It's labeling this as the 5th term. This one I plug in, that gives me a negative 10 plus 7, which is a negative 3. So a sub 5, or the 5th term, is negative 3, and that's it. On the next one, I'm given a sub 3 here, and I want to find the common difference. I'm given a sub 3, so I'm given a sub 3 right here is an 8. A sub 4 I don't know, a sub 5 I don't know, and then a sub 6 I'm given as a 35. And there's a couple ways I can do this. I can do a little bit of guess and check and try to fill these in, or I can use my formula here for my arithmetic sequence, which is this. It's a sub n equals a sub 1 plus n minus 1 times d. And I can just solve for the d value because that's what I'm looking for here. If I use basically, I can relabel this thing. I'm going to call this my 1st term, my 2nd term, my 3rd term, and my 4th term, just because it makes it easier when I do this. And so now what I'm going to do is I'm going to use the 8 for a sub 1. The n values, now I'm using 4 terms, and that 4th term is the 35. So essentially, I'm taking the term I start with and the term I end with for a sub 1 and a sub n, and then I'm plugging in the number of terms that I'm dealing with, which is 4, for my n value. And now I can just solve this thing for d. So here I subtract the 8 from each side. So that gives me a 27 equals 3d. I divide each side by the 3. And I find out that d equals 9. And that's all this question is asking for. It's asking for that 9. But an easy way to check this thing is to plug it in. 8 plus 9 gives me a 17. Plus 9 is going to give me a 26. plus 9 gives me a 35. So now I know with 100% certainty that that d value is correct. Okay? If I look at the next one, it says to find the 10th term of the sequence. And really, you could start with this. And since it's an r value, it means I'm multiplying and multiply by 2 and get a 1/8. And then multiply by 2 and get a 1/4 and keep going all the way to the 10th term. All right, that would be one option here. The other option is to use your formula, a sub n. So I want the 10th term. So it's a sub 10 equals a sub 1, which is the 1/16th, times r to the n minus 1. And my r value this time is 2 raised to the n minus 1, which is 10 minus 1. Okay, so again, I'm using this formula. That is a terrible looking a. Let me try again. A sub n equals a sub 1 times r to the n minus 1. All right, and really this just becomes a job for my calculator. I just have to be really careful about order of operations here. I do the 10 minus 1 gives me the 9, and then I do 2 to the 9th, and then multiply by the 1/16th, and it gives me a 32. So the 10th term here is going to be a 32. The next one asks me to find the sum of the first 12 terms of the series. Again, I could identify the pattern here, and the pattern is that I'm multiplying by 3 each time. And I could just continue that pattern all the way out to the 12th term, and then go ahead and add all these together. Or I can use my formula being s sub n equals, that's going to be a sub 1 times 1 minus r to the n all over 1 minus r. And this time I'm looking for the 12th term. So I could just plug this in and say a sub 1 is the 1/9. I've got 1 minus r, which is the thing I was multiplying by each time, which is the 3, raised to the 12th power all over 1 minus r, which once again is the 3. And this just becomes a job for my calculator. Again, I have to be very, very aware of order of operations here. I want to do 3 to the 12th power first. Then I want to do 1 minus that value, then multiply it by the 1/9. And then divide it by the -2. All right, and it gives me 29,524.4 repeating forever. But keep in mind 0.4 repeating forever is just 4/9, which is a nice accurate way to write this thing. Okay, and that's it. If I look at the next one, sigma notation or summation notation. Remember, it gives me the starting value down here. That's what I plug in first. Gives me the ending value up here. So I start off by plugging a 1 in. When I plug a 1 into this thing, it gives me a 3. And then I'm going to add the next term. I'm going to plug a 2 in. And when I do that, it gives me a 5. And then I'm going to plug a 3 in. And when I plug a 3 in, it gives me a 7. And then a 4 in. And then a 5. And then a 6. And then the last thing I do is plug in the 7. And that's where I stop. It's an ugly looking 5. Let me try again. That's where I stop because that's the stopping value. I started with a 1. I end with a 7. And now this is just a matter of adding these guys together. So I'm going to add these up. Here I get a 20. There's another 20, so that's 40. 63, it appears. Okay.